Hello everyone, so this is the second part of the rotational motion lab, and this part deals with the roller coaster track and the loop track, and here's where we're going to try and find what's called a critical speed. So the critical speed is the speed at which this ball, this little steel marble here, is when it hits this point, so the peak of this curve right here, and it's just ready to lose contact, right? Just ready to come off of the track here. That's going to be what we call the critical speed. So what we want to do is we want to measure this experimentally using the photo gate here. And we also want to measure it theoretically. And if you look in the lab handout, I derived the formula for the theoretical calculation. Basically, the theoretical calculation is based on the radius of this curve. So I have to know the radius of this curve right here, which is our trace. And ultimately I can find the radius of the path of the center of mass of the ball. So using the radius of the path as it goes over this point right here, this peak point right here, and using g, it turns out it's a square root of r path times g. That's going to give me theoretically what that critical speed should be. But what I want to do now is also compute that critical speed experimentally. Okay, so how do we do that? So first thing I did was I adjusted the height of this so that the ball here is just ready to leave the surface at that point. So you can kind of see how it just was ready to leave the surface at that point. And if I want to calculate the speed right at that position there, we're going to do what we've done in many labs in the past. If you guys remember the ball drop experiment, we had to calculate the speed at photo gate A and photo gate B. What we really want to do is calculate the speed right at this photo gate, right at this point here. So what I'm going to do is collect the time it takes, so using the CPO timer, the time it takes the ball to pass through the photo gate. And then if I know the diameter of the ball, I can take the diameter, which is like its displacement, divided by the time it takes to pass through, and that's going to be a really good estimate of the velocity at that instant. Okay? So basically what I'm going to do is 10 trials. So the trials look like this. I collect the time, so 0.0150 seconds, so 10 trials. I'm going to average that time and then take the diameter of the ball divided by the average time, and that will be our critical velocity experimental. Okay? Then we're going to do exactly the same thing with the loop track. So let me take this off. So here's the loop track. I already know it's right around here. This position will work best. So again, I adjusted this previously so that I know that the ball is just ready to fall off the track when it reaches the highest point on the loop. So when it reaches right here, it's just ready to come off. And again, I want to measure that critical speed, right, the critical velocity, both experimentally and theoretically. Theoretically, it depends on the curvature, the radius of curvature again, right, so that's in your handout. And experimentally, I did basically the same thing, except now I have to put the photo gate upside down. So right at the peak here. And then I'm just going to get the time for 10 trials as this ball passes through that photo gate. Okay, so in this case, it's around 0.0183 seconds. That's the time it takes to pass through the photo gate. And just like before, diameter of the ball divided by the average time should give us that critical velocity, right, at that instant. Okay, great. Hopefully that made sense.